So now, let's spend a little bit of time on linear programming. All right, so if you've fallen asleep already through network flows, I wouldn't blame you. But I recommend you waking up now, because this really will be useful in your life to know, maybe not to know how to solve this algorithm, because I'm actually not going to give you the algorithm, but knowing that this algorithm works is something that industry does. It's sort of bread and butter for industry. All right? So what's the problem? So I actually was a co-op student at Waterloo, and I had a co-op job, which was to make hot dogs. Right? And how do you make hot dogs? Well, there are thousands of linear equations, which they wouldn't tell me because I didn't have the clearance. But they tell you how much moisture and how much protein, what you can put in a hot dog, right? And then, given today's prices of all the ingredients, thousands of possible ingredients to go in your hot dog, the goal is to find what to put in the hot dog today to minimize the cost of the hot dog, and it's still being a hot dog, right? So I would, being the young hippie, would say, hey, guys, that's gross. And my boss would say, no, we're getting a cheap product to the masses. We're feeding the masses, and they claim a healthy product that's inexpensive. So you could go either way. So here, let's talk about mathematically what the problem is, right? So you have various ingredients, and what are we looking for? The solution will tell you how much of each ingredient to put in your hot dog, right? X1 is how many grams of pork to put in, right? Right? And then here are the costs of each ingredient. Right? I don't know why it shifted a little bit, but here the cost of pork might be 29 dollars per gram or something. That would be expensive pork. Very expensive pork. That's your gold standard pork. All right? So given that, you can calculate the cost of a hot dog, right? It's the number of grams plus the price per gram, or maybe it was the number of tons plus the price per ton, and you add it up, and you get the cost of a hot dog. Right? Everybody good? And then we have all these constraints, right? So this constraint might be saying how much moisture is there in a gram of pork, and how much moisture is there in a gram of grain, and so forth. Right? So you add up the total amount of moisture, and the moisture can't exceed this. Right? But it can't be, then you have another one which says it has to be at least something. And if you see, these are all less thans, but if you want a greater than, you just multiply through by negative. All right? Everybody buy that? So these are all the constraints that you have to satisfy, right? And how do we abstract as we remove the topic of the hot dogs? And so what you need to know is that linear programming is you have a bunch of linear a number of variables that you're trying to find real values for, and you have various linear constraints, and you're asking, give me the real values that meet all these constraints and maximize or minimize the constraint function, right? And turns out there's a polytime algorithm for this. And I told you already that often when you have integer programming, right, if all we changed on this was that these x's needed to be integers and not real numbers, then it suddenly is hugely NP-complete. It's just we don't have an algorithm for it, right? So, in fact, most problems that industry wants to solve that are NP-complete, you can express it in this way as an integer program, right? And you could relax the constraint that they're integers to being reals, right? So that's where I was joking that you only want to marry one person, but the solution that comes back might have you marry half of this person and half of that person, right? So, right, so now actually here's another funny twist about this story is that I was going to say, well, until I was a grad student, the best algorithm known was exponential time in the worst case, but in practice it worked really well. And then at some point while I was a grad student, they came up with a polytime algorithm for it. But the polytime algorithm is actually not very practical. People don't use it. People use the fast algorithm that could be. All right, so, here's another question that I have asked on exams, and most people get wrong, right? So I ask, express network flow as a linear program. All right? So here's the answer, right? Remember what network flow is I have a graph and capacities, right? Well, what are my variables? For every edge, I want to find the flow through that edge, right? And what am I trying to maximize? I'm trying to maximize the flow out of S minus the flow back, right? So that's just a linear constraint, a linear thing I'm trying to maximize. And what are my constraints? Is each edge flow can't exceed its capacity, right? So that's a linear constraint. And another constraint is that it's got to be greater or equal to 0. So that's another linear constraint. And this constraint says is an equals instead of a less than or equal to, which actually makes the problem easier, not harder, which says the total flow into a node equals the total flow out of a node. Right? So these are all linear constraints. And so network flows is an example of linear programming. And in general, in linear programming, is you have a linear program as a primal, you can take its dual, and if you take the dual of this, you get min cut. And so, yeah?
Just a quick question. You said we have to express network, we may have to express network flows as a linear program.
Uh-huh.
Are you allowed the min function to be able to express that, or when you make your thing?
Well, here I got max.
Okay, so yeah.
Yeah, the goal is to maximize this. This is a linear.
But what I'm saying is if you have two types together,
right?
You're trying to maximize the min of the, I guess. Oh wait, no, because that's just the capacity.
Yeah, I know these are just linear constraints. Maximize the flow subject to these constraints. It's just the linear program, right? Everybody kind of buy that? So let's try to picture. I've covered this algorithm in the grad class. Actually, I took it in course from my father, right? So you can suppose instead of 1,000,000 variables, we only have 2 variables, right? So each spot here is a solution, right? It's a value of x1 and of x2, right? If we have 2, we only have pork and protein and grain, right? So then every constraint is a line which says, well, the solution has to be over there, right? All of those constraints. And the objective function says we want to travel in this direction as far as possible, right? So you can see the optimal turns out to be this point up here, right? People kind of visualize that? And of course, when we have n variables, we have n dimensions, and each of the constraints is in -1 dimensional plane. And anyway, what's the algorithm? The hill climbing algorithm is I have a solution. And when I take a step is I loosen here. This constraint is tight. And if I move along here, I'm loosening this constraint. And I slide along this edge until I get maybe to this point here. And then that tightens this constraint. So it's right, let's look at here. It's a better picture. If I'm here, then this constraint and this constraint are tight. And to slide along this edge, I loosen this constraint, and then I move till I tighten that constraint. And that's called the pivot. And you keep doing that until you get up to here. And when you're up here, you can't pivot anymore to get a better solution. And then somehow you form a solution to the dual. and you're good to go. Everybody kind of buy that?
How does this look like in like actual like
In dimensions?
in like God?
It's pretty short code. I don't know. That's just I turn the dual upside down to give you, and that's it. Everybody good with that? And what? We're going till 4, right? So we got another 20 minutes. Yeah. That was one of my exam questions. Anybody want to say? Suppose you're doing linear programming, right? Let's go back here. Linear programming.
Well, you said when you can't pivot anymore.
You keep getting a better and better solution to the primal, right? And then I don't know how to take a step. I can't pivot to get a better solution to the primal. How do I prove that this is optimal? The dual. What do I get from the dual? I get a solution to the dual with equal value, right? We don't even know what the primal is, right? If the primal was choose which fruit to buy in order to maximize your health given your financial constraints, then the dual would be what vitamins do I buy in order to get the same quality of health as buying the fruit. There really is this amazing sense of flipping everything upside down, right? Instead of buying fruit, you're buying vitamins. Instead of maximizing cost, you're minimizing, I forget what, right? There's this weird sense of, but in any case, one thing that's true about the solution to the dual, any solution of the dual and any solution of the primal, the dual is going to be better, right? So that means that when they're matching, right, when your primal and your dual have the same solution, the dual solution witnesses the fact that you could never be better. Witnesses that globally you can't be better, right? Remember that? Here, let's go to my primal dual problem, right? Where's my primal dual problem? There it is, right? The primal problem is a place to stand. The dual problem is the roof, right? No roof is below any place to stand, right? So what do? I keep getting a better and better place to stand until I get a matching roof, right? Now I have a place to stand and a roof that are equal. I have a solution to the dual and a solution, right? The dual, the primal is maximizing some value, and the dual is minimizing some value. And the max primal equals the min dual, right? And when you find this matching, the primal tells you, it gives a witness that you can achieve something that's good for the primal, right? And the dual witnesses the fact that no primal can be better. Right? Does that make sense? Right? Let's get that nice sentence that I like here, right? Our location witnesses the fact that you can achieve this location, this quality of location, right? And the roof witnesses the fact that no location could be higher, right? So the answer to your question is, you asked, how do you know that the solution to my primal is optimal? Is, well, I have a solution to the dual which matches it. And they're equal. And the dual witnesses the fact that my primal can't be better.
Was that 2D thing with put on the screen, the line?
Yeah. It is exactly the same. Here, the place to stand is the primal. The dual is the roof. The place the primal is the flow, the dual is the cut. The primal is what fruit to buy, the dual is what vitamins to buy. Right? It's kind of fun to look at linear programs and look at their duals and see, oh yeah, they really do feel like complementary problems. And you're asking about this graph, right? Oh, we are way past it. Way into the nether zone, netherland, right? So in my grad class, I have a three-dimensional picture. But, you can imagine, you go to some hippie concert and they have a dome, right? And the domes are made out of triangles, right? And each triangle is a constraint. And you have a direction that you want to go. So you follow the pipes of your dome until you get to the optimal. And how do you take a step? Is you're on one intersection, of these edges, of these triangles, and you slide along an edge by relaxing one triangle and tightening up another triangle. Right? Linear programming. Everybody good? And if you go to any math package of any worth, whether it's R or, I don't know, Alfred Wolfram or Maple or probably even Excel. I don't know about Excel, but they'll let you do linear programming. Yeah, I don't know how to represent the dual. That's why I did the roofs. I wanted a visual picture. Everybody good?